Hey, welcome back to Math with Patrick. Today is November 14th, and we're solving problem 318 from the Daily Epsilon calendar. And the answer today should be 14 because that's today's date. So we have three integers. X, Y, and Z are elements of the integers, specifically integers greater than 0, or the positive ones. And X, Y, and Z satisfy two different equations. If we add them all up, we get 490. And then if we do 9 times x plus 11 times y plus half of z, we also get 490. Knowing that they're all positive integers, I think this means that z is probably the biggest of them all. That's just because if we take away half of z and then put in a whole bunch more x's and y's, we still get the same number. So that doesn't really help us solve the problem today because x is supposed to be 14, but just something to keep in mind that z is probably the biggest of them all. I think the first thing that I'll do here is multiply this bottom equation by 2. That way I'm lining up the coefficients on my z number rate or z variable here. And then this lets me use elimination to get rid of z. Knowing that the sum of x, y, and z is the same as 490, I can just subtract the sum of x, y, and z, or just take away x, take away y, take away z, and that's the same thing as taking away 490 from the other side. So we get 17x plus 21y, and then z minus z is 0, so we can eliminate that variable, and then we're back to 490 again. And here's where it's important that x and y are integers, because just with this equation with real numbers, there's going to be an infinite number of solutions. We could find kind of like the y-intercept by setting x to 0, dividing both sides by 21, so we can get a positive y-intercept, likewise get a positive x-intercept. And so we have all of these potential solutions in the real numbers. And apparently, somewhere along the way, we have some integer or whole number that also gives us a solution. Since we're solving for x, I want to somehow get rid of y. And the way I'm going to do this is with modular arithmetic. The idea here is that y is being multiplied to 21. So we have some amount of 21s in this number. And then the leftover amount is kind of recouped by adding a whole bunch of 17s. Modular arithmetic helps us out by essentially assuming that every single multiple of a given number, here I'm going to choose 21, is the same thing. So that means if I encounter the number 42, I'm going to assume it's the same thing as a 21. If I encounter an 84, that's also 21. Actually, if I encounter a 0, that's also a 21. Any of these numbers that I have, any of these multiples of 21, are just considered to be 0 in modular arithmetic, at least in mod 21. And this is going to help me, at least hopefully, dramatically simplify my problem here. I'm trying to get close to this 490, and I think it'd be pretty quick to jump up to 420, maybe add on another 42, and then I guess add on another 21. And so I can see that I could take out a whole bunch of 21s from this number. Technically, it's just a whole bunch of zeros. Maybe a little bit weird if you haven't worked with modular arithmetic before, but in this kind of system, 490 is just going to be the same thing as the number 7. The idea being is that 7 is 7 more than 0, just as 490 is 7 more than 483. So these numbers are technically the same, and I'm going to use this kind of triple equal sign, this congruent to symbol, to just say that they're kind of equal. Anyways, so in mod 21, 490 can turn into 7. This 21 times y is effectively 0 times y, so I can ignore it. And then I now just have 17x on the other side. Ideally, we isolate x and get 14 for today. So normally if this were an equation, I would just divide both sides by 17, but division doesn't really work so well in modular arithmetic because 7 over 17 doesn't exist here. Again, we're kind of working only in integers or whole numbers. And so I'm really expecting a number that's 0 through 20 and nothing else. And again, integers, not fractions. So instead, I want to find some number where I can multiply to both sides with the goal that this number right here turns into the number 1. Effectively, it's like I'm dividing by 17, but with modular arithmetic, we got to think in terms of multiplicative inverses rather than just dividing. Anyways, 17 times 5 is 85, and you'll notice it is 1 more than a multiple of 21, so it is congruent or essentially equivalent to just 1. And to keep my equation or congruent statement balanced, I should multiply the other side by 5. We do get 35, which isn't really a number in mod 21. I do need to scale this number back a little bit, so I am between 0 and 20. And so now if I just take off 21, we can see that x is congruent to 14 mod 21. And this essentially is my answer, but we should go back and double check and see what happens to all the other numbers. So let's see what happens if x is equal to 14. Well, we could try this equation right here, and I'm just going to use a calculator for this one, so I don't really need to worry about the arithmetic in my head. If x is supposed to be 14, then multiplying it by 17 gives me 238. Subtracting the 238 from 490 shows me that 21y should be equal to 252. Dividing that by 21, we get y is equal to 12. And then plugging in the 12 and the 14 into this equation, I can then subtract the 12 and subtract the 14 and get z is equal to 464. And I guess if you really wanted to, you could plug in these numbers. X is 14, y is 12, and then z, the biggest one, is 464. This should also turn out to be 490, and maybe you can try that for yourself. So we found the answer, though. X is 14, and I think we're all done. So thanks for watching, and I'll see you tomorrow. Bye.